just exactly how we would fit this, all the mathematics of a trajectory onto the Eniac.
What other applications did you have to work on?
Other applications?
Well, you said that you didn't do trajectories ever.
That's right. Well, the very, very first problem, the very first day that the Eniac was finally declared, it is now ready to work, although it hadn't been fully tested. Our test will be the feasibility of the H-bomb. It was a tremendous, tremendous problem that had been brought in from Los Alamos. It was Dr. Fermi and Dr. Teller's problem, and it was the feasibility of the trigger which they had designed. And so we put that problem on the Eniac. Now, someone had asked us a little while ago about the tubes and the reliability of them. There were many tubes that failed, but the Eniac was built in such a way that a tube did not have to generate a certain amount of power. There's a vacuum tube I'm talking about, which were in those days were pretty large. They were about 5 inches tall, each one, and there were 18,000 of the in the Eniac, which generated a tremendous amount of heat and everything. And these tubes were not operated full power. They were either any amount of power would turn them on, so they only operated in an on or an off position. If they were on at all, they transmitted the power. If they were off, they didn't. And that was the basic thing. So when we first started to operate the machine, we found out that there were a number of tubes that had actually failed, and another bad solder joints that had gone on and so on. And once those things got ironed out, the machine was really quite reliable, and it operated very well. So the problem that came from Los Alamos at that time, we did not program it. The physicists who came from Los Alamos had actually programmed it. They had studied all about the Eniac because they had top secret clearance, and they were able to have access to these wiring diagrams before we did even. Mm-hmm. And so they were able to program it, and we helped them, all of us girls, girls we were called in those days, all of us helped them program it and help them run it. It took about 2.5 months. And I don't know what it proved about the atom bomb, I mean the hydrogen bomb, whether the answer was yes or no, it was that the trigger was feasible or not. I have no idea about that. But what we did find out was that the Eniac actually worked, was actually reliable, actually did everything that was planned, and it looked like no matter what problem you put on there, the Eniac would eventually be able to solve it. So on the 15th of February of 1946, they had a huge demonstration and announced to the world, yes, that this machine worked.
So the first feasibility study of computers.
I can't hear you.
The first feasibility study of computers.
Yes, yes.
The first feasibility validation. Jean, how did you feel at the time of what you were working on, and how much did you have to understand what was being done, the application itself?
Well, the Eniac we knew because we'd all calculated them over and over. I mean, the trajectories we knew because we all calculated them over and over again, so that wasn't a problem. Our problem from the very beginning was finding out how to fit this problem on a machine with these switches. And, you know, we had to learn how to reuse code. They had something called a master programmer so that we could iterate a program you know, any number of times, and then after we'd done it, we could go do something else. We also could check the sign of a number, whether it was plus or minus. So we could arrange that, you know, that would be the if-then statement or whatever it is. Well, anyway, let me go back, though, to something that you brought up before about the reliability. When when Press and John first proposed the Eniac, all the professors at Penn, at the Moore School, and everyone else they talked to said they were nuts to think that they could use vacuum tubes and have them reliable enough to build a computer out of. Well, Press Eckert was all of 24 years old at that time, and a hotshot engineer. Well, Press Eckert said, I don't believe it, I can do it. Now, how could he do it? And that was by running the vacuum tubes at 50% of their capacity, so that they did not have to work very well. And as she said, they ran them as either they were off or on. So he designed it in such a way that if 50% of the tubes weren't working at full capacity, the machine still worked. Now, the trajectory problem was a very, very important problem for us. First of all, it was the acceptance test of the Eniac. The second thing was it trained us to program the Eniac. We had 2 of the women that were part of our team to calculate a trajectory exactly the way the Eniac did, so that it was a test to debug it, because we knew exactly at every stage of the calculation what the numbers should be.
So you actually...
So we could diagnose
run.
it down to a test tube.
So you could,
down to a vacuum tube.
So you would actually break it up into sections that you would manually compute.
If we were having problems. Now, then this standard trajectory, the way we assumed that our answers were correct, before we ran the problem, the real problem, we ran the test trajectory. And if it were correct, then we ran the real problem. Then we ran the test trajectory again. Now, if both test trajectories turned out correct, then we assumed the one in between was correct. And that worked very, very well. And it was quite a while, I would say, before the professors at Penn and people everywhere really believed that the Eniac could work and would give worthwhile answers. And it certainly did, because it was in use for 10 years, and Barclay Fritz has enumerated 100 scientific problems that it actually calculated. So, it did work. It was not just a publicity stunt or anything like that.
As programmers, start off with Kay. What was the most interesting program you had to do on the computer past the feasibility?
The most interesting program?
Yeah.
Well, for me, shortly after the Eniac was announced, the university began to get calls from all over the world, people writing. They finally had heard that there was going to be this wonderful machine. And before that, prior to that, when all computing was done either by hand or with a desk calculator, people had problems that they would like to solve. They called them 100-year problems. They would take so long to do that they knew they'd never be able to finish them in their lifetime. And all of a sudden, here was a machine that it was a 100-year problem, and thing went 5,000 times as fast as any other machine. You'd be able to do this in less than a year, obviously. People who had pet problems of some kind decided to write to Penn to see if they could be privileged to operate. So one of the problems, and the one that is most memorable to me, was brought there by a Professor Douglas Hartree from the University of Cambridge in England. And he had a pet problem that he had been working on for years, and it had to do with the airflow around like the wings of an airplane or something like that. So he had devised some wonderful calculations, and he had been doing these by hand. He said whenever he traveled on the train or anything like that, he'd always get out the notebook and keep working on this compressible boundary layer. And so when he heard about that, he wrote to the Army, I suppose, and asked permission to come. So he came with his problem, and so I was assigned to work with him and to help him decode his problem. And that was most memorable because he was a wonderful, meticulous kind of person. He knew an awful lot about computing. And in those days, people didn't know so much about computing. We did months of study just to find out how roundup error built up. And there were various mathematical problems that became involved in that. But that to me, oh, I had one final note on that. In November of this past year, Aberdeen Proving Grounds had a big celebration to celebrate the 50th anniversary of acquiring the Eniac. And lo and behold, they have, since the Eniac, acquired a number of faster and faster and faster machines. And do you know that they are still working on that compressible boundary layer problem?